All computers operate in the binary system. They do this because at their most basic, computers are just millions of electrical circuits connected together. Electrical circuits can only exist in one of two states: on or off, powered or not powered. Binary numbers only have two digits, ones and zeros, so binary is well suited to the two-state nature of electrical circuits. In computers, a circuit that is on represents a 1, and a circuit that is off represents a 0. There are three number systems we'll look at. The first is binary, or base 2. It only has two digits, 1 and 0. The next is the decimal system, or base 10. It uses the digits from 0 to 9, so it has 10 digits. Humans typically use the decimal system, and it's the system we're taught in elementary school. Finally, we have the hexadecimal system, or base 16. It uses the digits from 0 to 9 and letters from A to F. That gives it 16 digits. To understand how the different systems work, let's see how this number of dots is represented in each of the different number systems. You might take a look at it and say that there are 28 dots, and you'd be right, but only in the decimal system. Before we begin working with different systems, we'll need a convention to help keep us from getting confused about what number system we're working in. To do that, we'll use a subscript 2 to denote binary, a subscript 10 to denote decimal, and a subscript 16 to denote hexadecimal. First, we'll look at the decimal system. The decimal system is base 10, meaning each place value represents a higher power of 10. You can see the same dots we had earlier here on the left. There are 28 dots in total if we are using the decimal system. All that really means is that there are 2 10s and 8 1s. You can see this in the table in the middle. Each place value in decimal represents a higher power of 10, starting with 10 to the 0, which is 1, or the ones place. There are 8 1s plus 2 10s, which gives us 28. You can also see this on the right, where I've rearranged the dots to make it more clear. The decimal system is, again, the system that humans think in. It uses the digits we are familiar with, 0 to 9. Just remember, each place value represents a higher power of 10 in base 10. You have the ones place, the tens place, the 100s place, and so on. 1 is 10 to the 0, 10 is 10 to the 1, or 10 to the first, 100 is 10 to the second, or 10 squared, and so on. You'll see that binary follows the same pattern with 2 and hexadecimal with 16. As mentioned earlier, the binary system operates in base 2. That means each place value represents a higher power of 2. Here you can see the same dots that we've been working with, 28 dots. In binary, there are 11100 dots, not 28 as there are in decimal. Just look at the table in the middle. In binary, each place value represents a power of 2. So instead of a 1s, 10s, 100s, and 1000s place, you have a 1s, 2s, 4s, 8s, and 16s place. 28 can be thought of as 116, 18, and 14. That's why 28 in decimal can be represented as 1, 1, 1, 0, 0 in its binary equivalent. Just look at the expansion on the right if it's not clear how these two are equivalent. 2 10s and 8 1s make 28, just like 116, 18, and 14 make 28. The two systems are equivalent ways of expressing the same amount of dots. The binary system is the number system that computers use to perform all their calculations and instructions. At the most fundamental level, all data in programs are stored in a computer in the form of ones and zeros. Each 1 or 0 is referred to as a bit, 8 bits make 1 byte, 1,000 bytes make 1 kilobyte, 1,000 kilobytes make 1 megabyte, and so on. The last system we'll look at is the hexadecimal system. It operates in base 16, which means each place value represents a higher power of 16. Here, once again, you can see the same amount of dots. There are 28 dots, but that representation is in decimal. To represent it in hexadecimal, look at the table in the middle. You can see that instead of having ones, tens, and 100s place, you have ones, 16s, and 256s places in hexadecimal. In order to represent 28, just recognize that 28 is made up of 116 and C1s. Why C1s? Well, hexadecimal has 16 digits. Keep in mind that this includes the normal decimal digits 0 through 9, but it also includes the letters from A to F to represent the numbers 10, 11, 12, 13, 14, and 15. Going back to the table and the expansion on the right, you can see that 28 is made up of 116 and C, or 12 ones. 16 plus 12 equals 28. 16 plus C equals 28. In computers, the hexadecimal system is used to represent text like the characters in the alphabet, or punctuation, or numbers. This huge hexadecimal number you see here represents the words computer science. Finally, we'll see how to convert between the systems. Converting binary to decimal is fairly easy. Just remember that each place value represents a power of 2, starting with 2 to the 0 at the far right and increasing as you go left. Look at the binary number on the slide. By splitting it up into its individual digits, I've matched each 1 or 0 up with its place value. Just sum up each place value times its respective digit. You can see this in the expansion to the right. 1101 in binary means 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1, which equals 13. It's the same principle with hexadecimal, just a little bigger numbers. We're given the hexadecimal number 4CF2. Just remember that this means 4 times 16 to the third plus C, or 12 times 16 to the second, plus F, or 15 times 16 to the first, plus 2 times 16 to the 0, which is 1. Work out that math problem and you'll see that 4CF2 in hexadecimal is 19,698 in decimal. Converting between binary and hexadecimal is considerably easier because of the fact that we can take advantage of the mathematical similarities the two systems share. Just refer to the chart on the right and you'll be able to just replace hexadecimal and binary numbers in a one-to-one fashion. Take a look at the two examples on the left. To convert 30E to binary, we see that 3 in binary is 0011. So you just replace the hexadecimal 3 with the binary 0011. 0 is 0000, so you replace it with 4 zeros. Again, we look at E. E is 1110, so we replace the hexadecimal E with 1110. Taking those three numbers in order, we have that 30E in hexadecimal is equal to 001100001110 in base 2, or binary. You just reverse the process to go from binary to hexadecimal. Just break the binary number into groups of 4, starting at the far right, and replace the groups of 4 with the corresponding hexadecimal number you find in the chart. 1001 is 9 according to the chart. 0010 is 2 according to the chart. And finally, 1011 is B according to the chart. Keep this chart in mind, and converting between binary and hexadecimal will be very easy. That's all on number systems. Make sure to check the description for the link to the next video.